In this video, we'll continue our discussion of multiple linear regression. Now, just like before when we had simple linear regression, we can still do an ANOVA table for multiple linear regression. The formula for the sums of squares are going to be the exact same as before, where we have the y hat minus y bar squared, the y minus y hat squared, and then the y minus y bar squared. Now these are all in scalar form, and their matrix forms are something that we've talked about in the matrix video. The degrees of freedom depend on the model. Now we always have n minus 1 total degrees of freedom, but the model degrees of freedom is going to be the number of independent variables in the model, which is going to be p minus 1, or the number of parameters minus 1. So again, this is the number of independent variables in the model. That's the model degrees of freedom. Now this assumes that each variable has at least one term, but sometimes when we have an additional, let's say we have an independent variable, but then we have that independent variable squared, that will have additional terms for that particular variable. So let's look at the below case where we have x1, x2, and then we have x2 squared, and then the interaction between x1 and x2. So this is a polynomial, and it's got an interaction. Now we're going to have a degree of freedom for each of these additional terms as well that we're estimating. So this is going to be, we have 1, 2, 3, 4, so we're going to have a degrees of freedom of 4. Now you can think about this another way, just looking at the number of parameters that you're estimating in the model. We're estimating B0, B1, B2, B3, B4, and then we subtract 1 from that, so we have 5 betas that we're estimating, and then subtracting 1 from that gives us a degrees of freedom of 4. Now the error degrees of freedom is, as always, just the difference between the total and the model degrees of freedom, which is going to be n minus p. And again, p is the number of parameters that we're estimating in the model, not sigma squared, that's not in the model, but the number of parameters that we're estimating in the model, and p minus 1 represents the number of independent variables because the intercept isn't an independent variable. As before, we get the mean squares from dividing the sum of squares by the degrees of freedom, and the mean squared error is still always and forever will be the estimate of sigma squared. So for our ANOVA table, this should look extraordinarily similar. It is exactly the same as what we had before. The only change here is the degrees of freedom. The regression degrees of freedom, instead of now being 1, is p minus 1. The error degrees of freedom is n minus p instead of n minus 2, and the total degrees of freedom is n minus 1. Note that when we have a simple linear regression, p is 2 for a simple linear regression, and this all simplifies to the same ANOVA table that we had for our simple linear regression. Just like before, we can implement the F-test for model significance, and again, the general linear F-test is one of the most useful tests that you have. This is slightly different, but here we have the mean squared regression divided by the mean squared error. The difference from simple linear regression is in what we're testing. Now in simple linear regression, we were testing whether the slope parameter was 0 or not using the F-test from ANOVA. In this particular case, though, we're testing whether all of the parameters of the, all of the coefficients from the independent variables are 0, or if any one of the coefficients of the independent variables is not 0. So this is slightly different. It's testing all of our independent variable coefficients at the same time, as opposed to just the coefficient from the single independent variable, which was what we had in simple linear regression. Now because of this, just like in a traditional ANOVA, we don't know where the difference is going to be. So if we have a statistically significant relationship in the F-test from our general ANOVA table, this isn't going to indicate which variables are statistically significant. It's just going to indicate that at least one of them is statistically significant. Now it's slightly more complicated than that, but that's the general idea. Incidentally, in R, you'll notice that R actually breaks it down by independent variable. When we try to run an ANOVA on a model, we can collapse this back down if we really wanted to, but we won't worry about it because it's actually kind of handy to have it broken down by independent variable. Under the null hypothesis, the F statistic has the degrees of freedom p minus 1 and n minus p. Recall it has 2 degrees of freedom. degrees of freedom for the numerator and degrees of freedom for the denominator. We interpret the test statistic as always, and then if we reject, we conclude again that at least one of the explanatory variables or IVs is important. If we fail to reject, and the sample size is large enough, so we need some pretty strong statistical power to make any claims about accepting the null hypothesis. So we want to be kind of careful about that. But if we fail to reject here, then what we look at maybe isn't a determination that none of the explanatory variables are related to the dependent variable in the population, but at least that we didn't find that to be so. And so what this would actually practically mean is you may choose to run the general ANOVA test, and then if that general ANOVA test is statistically significant, that's when you go in and look at the coefficients. Quite frankly, practically, we never really do regression this way. In regression, we really just focus on we go straight to the parameter estimates for each of the parameters. We don't tend to do the general ANOVA. The exception is for what we've talked about in way back in chapter 3 or 4, where we talked about the general F test. Now that is extraordinarily useful with the nested models. All of that theory, actually nothing changes. We don't even need to talk about it again because it is all exactly the same for running with this case, except now you have a much larger grouping of models where you can have a full and nested model. Now we have r squared, the coefficient of determination, but now it's going to be a capital R squared because now we don't have a basic correlation that we can square. So recall that our previous coefficient of determination, we just took the correlation between x and y and squared it, but now we have multiple independent variables, so there isn't a single correlation between an x and y because there's multiple x's. Thus, we use the coefficient of multiple determination, which is actually the same as the coefficient of determination we talked about earlier, but it's formatted in a separate way. Now, instead of squaring a correlation, we talk about the sums of squared regression compared to the sums of squared total. Now, we did talk about this earlier in preparation for this moment when we couldn't just square the correlation coefficient, and you might have been curious about why we took that extra step. It's because here, again, we don't have a correlation coefficient to square. So using the sums of square regression divided by the sums of squares total gives us the same idea. The percentage of variance in the outcome that's explained by all of the variables in the model. Now what's interesting here is if I add a variable that is almost completely unrelated, or in the population is completely unrelated to the independent or to the dependent variable. So I just add a completely random independent variable. R squared will always go up. R squared never goes down when I add variables to the model. So the trick is that we can't use R squared to say, hey, I added this variable and the percent of variance in the DV went up. That was explained, so hey, this variable must help me explain more variation in the dependent variable. It doesn't work like that, and it's because even if I added in a random independent variable, the R squared is still going to go up, albeit slightly. And if it were perfectly independent from the outcome, it wouldn't go up, but even just the random noise is going to make R squared go up at least slightly. So when we're looking to add a variable and we want to see, well, does this variable actually help us explain more variance in the outcome? So I've got a model, I add one variable and I see, did the R squared increase? Again, it's always going to go up, so we can't use that as a metric to say adding the variable helped me explain more variation. Thus, we have an additional statistic called the adjusted R squared, which tries to give us a metric that we can use to say, well, if I add a variable and the adjusted R squared goes up, then that actually means that the variable did help me explain something. So recall that the mean squares, which is what we're using here, and we used the sums of squares previously, the mean squares are just the sums of squares adjusted by the degrees of freedom. So now all we're saying is that we want to adjust what we had before, the regular R squared, by the degrees of freedom, and thus we get the name adjusted R squared. The adjusted R squared is better from this context than the regular R squared because it can increase or decrease when a new variable is added, depending on if the drop in the error is offset by the lost degree of freedom. And because of this, we can use this to decide when we add a variable, if the R squared adjusted goes up, then that variable actually is useful. versus with the regular r squared. If we add a variable and the regular r squared goes up, that doesn't tell us that that variable is actually explaining more variation, because the r squared will always go up every single time. Now I should make a note here that r squared adjusted is just one of many statistics that we could use for this purpose. It's probably not even the best one. In fact, it is certainly not even the best one. So take it with a grain of salt. There's a whole field here. If we have our advanced regression course, or in our machine learning course, we talk about some of the other options that you can use. All right, so what if we want to make inference for individual regression coefficients? Well, we already have the distribution of the vector of parameter estimates. We know that the mean is the vector of population parameters, that is, that the vector of parameter estimates is unbiased. And the variance covariance matrix is the sigma squared times x transpose x quantity inverse. So when we're looking to create a variance of these terms to eventually get the standard error, the variance covariance matrix is the estimated variance covariance matrix, just replaces the sigma squared with the mean squared error, and we still have x transpose x quantity inverse. So this estimated covariance matrix is just a p by p variance covariance matrix for the vector of parameter estimates. Again, recall that this is the variance covariance matrix. So, and all of our equations use standard errors. So if we need to get standard errors from the variance, we just take the square root of the values in the variance covariance matrix. Now we can get the variance of individual estimates, bk. So bk is a single parameter estimate, the kth parameter estimate, and we can get the variance of that by taking the kth diagonal element. So that is that the variance of the kth parameter estimate is the kth row and the kth column entry of the estimated variance covariance matrix for the vector of parameter estimates. Well, that's a mouthful. Note that k goes from 0 to p minus 1, so this is the parameters, right? Beta sub 0, b sub 0, b sub 1, b sub 2, etc., etc. But for the matrix, it would be plus 1. So the variance term for b sub 0, and again, we take the square root to get the standard error of b sub 0, is the 1 by 1th entry in this variance covariance matrix. So 0 would be in the b subscript, and then 1 would be in the matrix, and so forth. So if I wanted the p minus 1, the variance component of the p minus 1th parameter estimate, then I would take the pth by pth entry of the variance covariance matrix estimated for the parameter estimate vector. Now, based on this, we can create confidence intervals for beta sub k. So the confidence interval is just the point estimate plus or minus the critical value, in this case a t statistic, times, and again, that square root of what we found previously. So this is the standard error component. So previously we talked about the variance. Recall that the variance of a parameter, the square root of the variance of a parameter is the standard error of that parameter. Critical values, just like before, come from the t-distribution with n minus p degrees of freedom, which is just the degrees of freedom of the error term. All right, so if the confidence interval includes 0, then just like before, we can't reject the claim, the null hypothesis, that this is that the that the parameter is itself 0. And we'd say this variable is not statistically significantly related to the outcome. Now the difference, and we're about to the end of our intro to multiple linear regression and jumping into inference and interpretation, but the difference in interpretation when we're dealing with multiple linear regression is that the interpretation is the regular interpretations that we had, comma, when added to the model containing all the other variables. So it's important to realize that as we interpret parameters and relationships in multiple linear regression, these interpretations happen in the context of the other variables that are also included in the model. So if the confidence intervals include 0, we fail to reject the null. That is, that this variable, the kth independent variable, is not statistically significantly related to the outcome when added to the model containing all of the other variables. So the significance tests for this parameter is known as the variable added last test, a technical term. The variable added last is just indicating that this is the last variable included to the model, so that we're testing this variable after we've already added all of the other variables in the model. So this is a conditional test conditioned on all of the other variables already being in the model. Think about our how we looked at multicollinearity. We talked about those little slices, and that's because when we're testing this, we take out all of the slice that's already been related to another variable. So when I look at any particular independent variable, it doesn't go, oh, the first one gets as much variation as it can, then the second one accounts for the first one, then the third one accounts for the second and first. Every single variable accounts for all the rest. So the first variable accounts for 2 through p minus 1. The second variable accounts for the first one and the third through p minus 1, and so on and so forth. So all the variables, we're testing them in light of all of the other independent variables already being in the model. Test statistic is just as before. We have a parameter estimate minus the null hypothesized value, which is typically 0, so I don't even list it here, divided by the standard error. And we compare to a critical value with n minus p degrees of freedom. Now this test, the variable added last test, is the one given when you just run the R. So if I run my linear model and then I take a summary of that linear model, that is what R is going to give me by default, is this variable added last test. And again, this is why multicollinearity is such an issue, and it's why it's so important to realize what we're actually measuring. Now, for some, this may seem like a really dumb decision. Well, why do I want to belittle my variable by including all of the other things? But actually in applied research, this is a very, very, very handy tool. So I'll just mention one case before we're done with this video. In a recent medical example, I was looking at actually we were looking at survival rates of patients on different drugs and wanted to see if using this particular drug increased or decreased the survival rate. The problem is that every patient who walks into our hospital is slightly different. They all have slightly different pre-existing conditions. They have slightly different injuries. They have slightly different comorbidities, such as body mass index. They're different genders, males and females. All of these patients are slightly different than one another, and those aren't what I want to test. I don't want to test as somebody who comes in with a higher body mass index more likely to die. I already know that that's the case. If you come in with a lot more comorbidities, it's going to be a much higher likelihood that we're not going to be able to help. What we wanted to test is the effect of the drug, not including all of this other stuff. So actually, a multiple regression is the perfect tool because I can include all of those other variables. And then I can drop in, well, it doesn't matter what order this happens, I can just include them all as a big chunk. But when I look at the parameter estimate for my drug, did I use drug A or B, I know that the significance of that parameter estimate is after taking into account all of these other variables already in the model. So when I declare that, hey, drug A works statistically significantly better for saving people's lives, that's after accounting for their injury score, that's after accounting for their gender, that's after accounting for their BMI, which is a fantastic conclusion and something that we really like to do in applied research. So this is very, very handy, and what ends up happening is that we may only have one independent variable that we care about, but we drop in many independent variables related to the demographics of individuals to indicate that our independent variable is still contributing to the outcome even after accounting for all of these dependent variables, or all of these demographic variables that we don't want to be included in our decision, or that we don't want to be messing up our decision. All right, well, in the next video, we will jump into continuing this discussion on inferences with multiple linear regression.